Thank you. It's nice to be here. First time here. I really like it. So the topic of my talk that I was given is GPDs from Lattice QCD, but I really would like to add some more a little bit if I have time. So since Nilmani already introduced the Lattice, I don't have to go to great details. The basic point I want to make that it's a non-perturbative regularization of a field theory. And the way we do it is we discretize space-time. The time is an Euclidean time, not the Minkowski real time. And then, as usual, we put everything which Nilmani already described. And the box kind of that it's a NS number of points in each space direction and in tau number of points in each Euclidean time directions. So if I take this and such a discretization, then typically the number of degrees of freedom, I will have this box size like NS cubed times n tau times color, spin, flavor, and whatnot. So any typical modern day calculations, that means that I have like 10 billion of degrees of freedom. And with this, integrating over this degrees of freedom, I want to compute the QCD path integral. So obviously that's not doable by computing by one person. And that's why we need to solve this and evaluate this numerically with the Monte Carlo methods. But even with the Monte Carlo method, it's not easy. So we really need big computers to do this. So this is to address anything that's related to EIC, we would need a computer like an exascale. So just to put something in perspective, what is an exascale machine? So imagine that each of the 8 billion people are doing one addition per second. So the amount of computing that one exascale computer can do in 1 second will take the whole Earth to do 4 years. So that's the kind of computing we need to address EIC physics. Okay, so again, going back to the point, Lattice is really designed to handle essentially non-perturbative field theory. And we know in many cases, since many of you are coming from the heavy ions, that we have, what we know is when lattice calculations, say the QCD equation of state at finite temperature close to TC, there is no, obviously, that I cannot take that describe this in terms of individual quarks and gluons. It's a strongly coupled field theory. Similarly, very recently, we've also done this calculations of how the heavy quark diffuses in quark-gluon plasma, the heavy quark diffusion constant. Again, if you really look at the close to the transition temperature, it is essentially very compatible with an ADS-CFT result. It's fully strongly coupled field theory. It's hard for me to, at this point, to sort of say from how I go from here to a descriptions, which is terms of individual quarks and gluons. However, in EIC, what we are doing is we are really exactly trying to probe or exactly trying to answer these questions. So what we are trying to answer, the big question is what sort of the partonic origin of proton mass, and for example, or the partonic origin of the gluon, of the proton spin. By partonic means I want to describe the proton mass and proton spin in terms of individual quarks and gluons, not a strongly coupled theory. So how do I do that? So this is a big question. How do I do that? It wasn't there for many, many years, and only very recently in the last 5-10 years, we have found the method, and we really know how to do this, and presumably I will try to convince by the end of this talk that now we are making great progress, and we really are there to handle it. So what is a partonic picture? The partonic picture, as you all know, it's a simplified or effective description, QCD. It's QCD as seen on by light. So it's a QCD in the infinite momentum frame. So it's an effective description, means I take the large momentum limit, the infinite momentum limit first of the QCD, and then after taking that moment, I get an effective theory, and then I regularize the my quantum field theory. On the other hand, what I do on the lattice is it's completely opposite. I regularize my field theory, and the only way then I can handle is by taking the large momentum limit later. So this I can do, for example, and since I'm on an Euclidean space, all my operators must be space-like. The separations of any two operators must be space-like. I have no other choice. So to do this, and to go to the Platonic picture, what I can do at most is I can take a space-like operator inside inside a hadron, and then boost the hadron. Then if the boost is very, very large, I am going to the infinite momentum, then in the rest frame of the hadrons, I can think that these operators are becoming more and more time-like. So that's the way I will handle, but again, the key question here is, in this context, and what I'm doing is I'm regularizing my field theory first, and then taking the large momentum limit. This is completely the opposite to what I do in a Platonic picture or in a parton model. I take the large momentum limit first, and then regularize my field theory. Now this is a field theory, so these two limits don't commute. So, but two limits don't commute means these are ultraviolet effects, and I can correct this non-commutativity of these two results in terms of a perturbative QCD. And UV physics, I can match and correct this just to make a hard physics, the perturbative QCD. So just to summarize the way it would be doing, we were going to handle this to see the parton physics from lattice QCD. I will take a state, I will boost it as much as large as possible, and then I'm all talking about normalized operators and so on, that's kind of taken care of. And then after I get that, then I will do a UV physics matching, a perturbative QCD, going from this large momentum theory to the parton model by UV corrections. Now this matching corrections, you can do either in the position space or in the momentum space. It's more or less completely equivalent, except for some power corrections, which would be different in different spaces. And these are sort of when I call matching. So what I mean is this PQCD corrections going from the large momentum theory on the lattice to the Platonic physics, which and match it to some experiments or other physics. In the talks, you will listen, you will hear sometimes the leading order NLO, NNLO, and so on. By which I mean in this context is I compute this matching coefficient, the matching in perturbation theory. So leading order means this is computed at alpha s to the 0, and NLO alpha s, and NNLO, even in some cases that we use at alpha s squared. And obviously the rest of the things, because I'm doing a PQCD, there will be logs. There will be logs of some typical scale with the factorization scale mu coming in. This typical scale, if I'm in the position phase, these scales are my resolution, like equivalent to q squared. Obviously, if I am in a position space, this is sort of the distance between the two operators that I'm choosing, it's z squared, and smaller z means an OPE, a smaller q, and I can do an OPE expansion. And if I'm in the momentum space, then this scale is actually 2 times x times pz. It's not pz, it's 2 times x times pz. It's kind of intuitively easy to understand. So because I'm on the lattice and the Euclidean space is essentially, if you're looking at a GIS, then you have to imagine a photon coming in with 0 energy transfer, but only a space-like transfer of 2px. It's kind of a bright frame parton going in xpz and coming back with xpz with the momentum transfer of 2xpz. Okay, so we all know, so as I said, that initially I want to go and understand something like an angular momentum as Nilmani was talking about. So angular momentum, obviously I need an momenta. So I need the momentum fractions of the parton and its distribution. And how do I get it? So that's kind of the 1D picture of a hadron. And how would I get it on the lattice? And just to be clarified, so I will take a hadron, and which has some spin and a boosted in the, let's say in the z directions, and then I will annihilate this hadron at a Euclidean time, so that I can only get the ground state of the hadron I'm interested in, as Nilmani was same. So in between at some point, I will insert the sort of this operator that I want, essentially in say in the quark case, the quark anti-quark field separated by a distance in the, say, the other, in the z directions along the line which hadron is boosted, because I wanted a collinear object in this context. And then, of course, this is connected through a gauge field, otherwise I don't get a gauge invariant object. Now, to get something like an angular momentum, in addition to the momenta, obviously I need, its angular momentum is r cross p, so I need the p as well as I need the r. So essentially what I really need in this context, what is a 2+1D snapshot of the hadron, where I need, which is called the generalized parton distribution, which not only tells me how my momentum fractions of a parton is distributed, but also how that distribution changes as I go to different locations in the transverse plane of the hadron. So the GPDs are functions of the space, the B perp, in the transverse space, and the factor x, and the x, obviously. Typically, the B perp, we look at the objects in terms of the conjugate of this B perp, which is the momentum transfer in this context between the two hadrons. It's the same as PDF, the only difference would be there is a momentum transfer between these, the initial and the final hadrons, and the rest. And this, the distance, this B perp, or the position, is nothing but the conjugate of this momentum transfer. Okay, so there are various kinds of GPD. I'm just as twist two, this is also not really twist two. So this is a spin half case. Let's just focus only the thing that I will probably just mention in the talks, which is this H, E, and H tilde. So H is nothing but if I'm looking at a distribution of an unpolarized, say, quarks in an unpolarized hadrons, the E, I want to look at a transversely polarized quark, unpolarized quark in a transversely polarized hadron, and H tilde is going to look at a longitudinally polarized quark in a longitudinally polarized hadron. But if I'm in the spin zero case, the only one that survives, like a pion, is this one, an unpolarized quark in an unpolarized hadrons. There are also transversely, it could also have a transversely polarized, but in most of the cases, this is a higher twist, which I'm not going to talk about those. Okay, the GPD calculations on Lattice is kicking off recently, and going to this level very recently. Mostly because it was very hard to compute. Kind of a technical breakthrough happened like 1.5 years ago, or a little bit a year ago. So what used to happen is when I compute and take a momentum transfer in this context between these two hadrons, so usually traditionally we used to choose that this momentum transfer is symmetrically distributed between the two hadrons. And that's a tough calculation in terms of, in this context, then you have to actually do calculations, separate calculations for each momentum transfer. There's technical reasons for that. Let's not go into it. So if I want, say 10 momentum transfer, I have to do 10 different calculations. Now, what we have found and developed in the last 1 year or so is a Lorentz covariance formalism. Of course, I want to look at GPD. It should not depend on frame. So I want to find eventually a Lorentz covariant formalism where I can compute in any frame. So we developed just a formalism and applied it where I can do this computations in an asymmetric, in a frame where the momentum transfer is asymmetric. And in this case, the easy thing, or the advantage, is that I can do like multiple, like 10 momentum transfer at one go calculations. And there are other technical reasons why there are more, it becomes more cheaper. And so overall, I can gain with this new formalism like a factor 20 or so. So that sort of enables in the last year into put us in the more perspective. And all the results I'm going to show today are all coming within the last year. So this is only the reason that we could go ahead and keep doing it now. Okay, so this is new. This is coming very soon. It's unpublished. I want to start with this because I want to set a few things on this. So this is a pion GPD, the GPDH, as I said, unpolarized quarks, unpolarized hadrons. And what is shown here is the GPDH as a function of x for different values of momentum transfer. So this, on the top, it's a zero momentum transfer, essentially the forward limit, the PDF, and going down to a momentum transfer of about like 1.7 GeV squared. And what you're seeing here is there are various things going on. And just to simplify, these bands are essentially what I'm getting the GPD with and then these are NNLO matching. It's up to alpha order alpha squared, but there are also some other resummations going on, which is called the leading renormal on resummation. That's sort of to correct some power corrections. So these are essentially for you to know this is NNLO level. And in this context, the solid bands, it is NNLO plus when I'm resumming the logs in the matching. Remember, I told you that the logs that comes in the matching in like the equivalent of Q squared observable is 2x times PZ. So for any given fixed PZ, if I go in a small x, then I get the logs become larger. So at some point, if the logs become larger, I don't trust this matching, it becomes untrustworthy. So just to see that effect where it does, this is nothing but a DGLAP log, equivalent of a DGLAP log. I can really resum those DGLAP logs, and these solid bands are sort of when I resum those DGLAP logs and match through this to see to what extent, to what x, I can really trust the difference between when these logs becomes large compared to NNLO and NNLO plus this resumming these logs. And at least for these values of momenta, which I'm using right now, which is 2 GeV or so, so from x equals 0.2, 0.1, 0.2, that's, I don't think one should trust that. At least that's what I would say at this point. Okay, so this is a state-of-the-art calculation with all bells and whistles going on, and most of the cases we don't even have this for protons. So this is really a benchmark kind of calculation where I wanted to start with. Now going to proton, so this is I'm looking at a proton GPD, so it's an unpolarized quark distribution, either in a unpolarized proton, that means I get the GPDH, or polarized proton, in this case, I get a GPDE. Now, all these calculations at this moment are done at zero skewness, which basically means the momentum transfer is just perpendicular to the boost of the hadrons, not along the directions of the hadrons. There are reasons we can do it. It's not technically difficult, but that's sort of the reason we wanted to start with. As I said, everything is within the last less than 1.5 years, actually. So this is GPDH, which is GPDE, and again, for various different momentum transfer going from the forward limit up to 2.5 GeV squared momentum transfer. So, of course, this is these are the things that we want to measure eventually in EIC or also going on in JLab. We can say, so what? So what's sort of the physics behind it? So this is I can answer probably what Raju was asking the questions. So when you look at an angular momentum in terms of the energy momentum tensor, if you just use the equation of motion on that, this is the reason why Jingdong actually probably first invented GPD, is to see that if you just use, this is just nothing but the QCD equation of motion, so you can calculate all the angular momentum, some rule and everything is just nothing but the fast moment of GPDs. So if you're really, experimentally what I actually going to measure is these GPDs and take the first moment, and then I will go to measure probably the spin sum rules and check the spin sum rules and etc. Otherwise, there is no way to access in experiment the energy momentum tensor itself. You have to do it through a DVCS and a GPD. So here is this A's, it's just a standard nomenclature. The first moment of H and B are the first moment of E. And then if you take this as a function, and you compute that and as a function of the momentum transfer, and the total, the G-sum rule, which is the total angular momentum contributions to the proton spin, is defined that the first moment in the limit of t going to 0. Of course, you cannot take the t going to 0 limit first and do the first moment. That doesn't work. So you have to take, in the experiment, you would probably measure and go to take the limit in that way. So, so if I just take this, and this is not the as sophisticated calculations what Nilmani was showing when you just compute it from the energy momentum tensor. So in this context, if you just take it, then you will find that 0.3 of the 0.5 are actually coming from the quarks, and the rest are, you have to take it the other contributions in this context, and the G-sum rules with the gluons. Okay, but we also said that we want to map the proton in this context. So this is like what Google does. If you tell Google to give a map of proton, but this is Google is a $850 billion market cap company, and which maps the whole world. But what we want to map is an object which is almost 10 to the power 22 times smaller than the whole Earth. So, but for that, we will do it in a much cheaper way, much cheaper than Google, obviously. So let's go to two specific examples of what we can do. So if I just take the A2 moments and do the Fourier transform, I'm just want to go the distribution in the impact parameter space. So this is nothing, or at least in some context, this is in one of the some rules. There's more complications to it. We can discuss that later. It's just called the enthalpy of the hadron. So this is what it will give you in this context. If I do this, is nothing but the distributions of the enthalpy of a hadron, of the quarks in the hadrons. Yoshitaka, and then the angular momentum, this is the G angular momentum, not the orbital angular momentum, of the total angular momentum. I can also look at the distributions of it. How does it arise, at what x, and how does it look like? Of a transversely polarized proton, the proton is moving at you and polarized along this to my left. So this is an example of what you can do and what you would get by doing this. So this is the up quarks. On the up row, the top row is up quarks, the bottom row is down quarks. To my left is the unpolarized or transversely polarized proton, and to my right is the unpolarized proton. And this would be the distribution. So these are the enthalpy, so-called enthalpy distributions of the up and down quark, and this will be the total angular momentum distributions coming from the U quark and coming from the D quark. So there few things are obviously, I mean, like just stands out. This is sort of because of this polarization, that's how angular momentum arises. Your up and down quark would be shifted, and also the up quark is symmetric, the down quark is distorted, the distribution, and this is sort of what gives you the chromomagnetic moments or something that generates it, sort of the Burckhardt kind of thing. The other interesting thing that you can see is in the scales. If you look at the down quark versus up quark, there is a scale in the distribution is around a factor 3.5. So it just basically tells you that for some reason the down quarks are more concentrated towards the center of the hadrons in this particular frame, and in the bright frame, whenever you can write down this distribution, and the up quarks are actually much more spread out in the hadrons at this values of, it's just the angular momentum. This is not an X distribution in this context. Okay, so Yoshi was talking about the spin orbit coupling. So let's get to the spin orbit coupling of the quarks. The spin orbit coupling of the quarks can be obtained in principle in the sort of hadrons or in terms of GPDs, as nothing is from the GPD H tilde or related to the GPD H tilde, which is longitudinally polarized quarks inside a longitudinally polarized hadrons. And there's some rule that from Cedric, Lars said, it's the spin orbit coupling in this context is nothing but the first moment of this H tilde distribution minus 1 that comes from the total, the H distributions, modulo the twist 3 corrections, which is the transversity. But this twist 3 corrections in this context is suppressed by the order of quark mass to the nucleon mass, so these are really, really tiny and small. So this is sort of the reason people want to look at GPDs or measure these GPDs is to go and find this physics, like what is the spin orbit coupling, what sort of the angular momentum and so on. In addition to, if you say, a 3D imaging of hadron. Okay, I am right on time, at least from my sense. So I just want to do some news flash of something which is not GPD, just because it came out yesterday in some discussions. So I'm not going to explain it too much, so it's just for more on the audience which are more expert. So this is the transversity distribution PDF of proton that we computed at NLO. So this is the U plus D, U minus D. This is the U plus D distributions. And I just want to show you how it looks like. So there are various different things. Let me go to the lattice results first. So there is a leading order calculations, which is this band, the red on the behind. There's a NLO plus some resummation, a renormal on resummation. And then there is NLO plus if I resum essentially the Diglap logs, how it looks like. And just to give you an idea to what extent in X, we can say that this is more or less trustworthy. And in terms of that, it is compared with, this is the JAM fits with this blue line, what JAM 3D 2022, it's a NLO, it's a leading order fits to this object, and as well as to Marco and Alessandro's fits are from 2018. Okay, Collins superkernel. So this is the Collins superkernel. That this one is really new. It's unpublished. I hope to publish it in a month or so. This is the Collins superkernel as a function of B-perp going up to B-perp of 1 Fermi. Now, let me explain what these are. So this calculation is done with a fully chiral quark, a domain wall, unitary domain wall chiral quark calculations with physical pion masses. So he's as close to physical that and control that we can get. Of course, it's not a continuum extrapolated and so on. So this is also possible because of a technical breakthrough which happened very recently. The problem, so let's look at these points, the blue points. So to do the Collins superkernel, of course, you want to do a TMD or a TMD with functions. You have large, long links. To calculate those long links on the lattice gets very noisy. So that's one of the reasons it gets so noisy and becomes uncontrollable. The larger B you go, longer the links become. So to avoid this, or to think about this, Yang Zhao, and we have been thinking about this to get rid of the link. So we could have computed in a fixed gauge, like a Coulomb gauge. The only difference is, the problem is, if I want to do it in a Coulomb gauge versus the normal thing, my whole matching completely changes. I have to redo the whole matching, and it has been done very recently. That's the reason we could have done this. So these black points are the very recent unpublished calculations that we did with this new method going up to nearly 1 Fermi of the perp. And this is another lattice calculation, kind of, in my opinion, my own opinion, the previous state of the art, coming from the MIT group and the Argonne. And so this is how it used to be like half a year ago. And this is our equivalent, the gauge invariant calculations. Within the large error, the gauge invariant and the Coulomb gauge will agree at short distance. And for the perspective of the other phenomenological extractions of this, so the blue one is Pavia's 2019 fit, this one, and the this band, the magenta one, is Shkimemi Vladimirov 19 fit of this. But if you really look at the real one, the really new ones, which is a MAP 2022 from them and the ART 23 from Vladimirov and company. So now you compare this with the lattice calculations. I find it very impressive, like even within the sort of the uncertainties and going up to 1 Fermi distances. Okay, I will end up with, in the next 5 minutes or 2 minutes, I will end up with a more intriguing thing. So this is sort of eventually at some point, as Raju was discussing, we want to go beyond single parton or just partonic. We want to go and see at some point some multi-parton interactions. This is the very simplest object. This is just a pion and kaon form factor, but going up to very, very large momentum transfer up to 30 GeV. I wanted to show this because there will be a talk on this, I think at the end, towards the end of this meeting on the measurements in JLab and EIC of this pion form factor at very large momentum. So these are the QCD predictions of the pion and kaon form factor going up to 30 GeV momentum square transfer. So this is the blue ones is the kaon, and the red ones are the pions. And for the low Q squared region where you have data like the pi and etc. from JLab, it has perfect agreement with the lattice results and so on. But the real thing is the large momentum. Now, if I have this is like an elastic scattering. So there's a pion or a meson. You hit it with a very high energy photon, like a 30 GeV core. Nothing happens to the pion, except it just changes its momentum and happily go through with a 30 GeV squared new momentum transfer. It doesn't break up. It's just a totally elastic scattering. So if I have a very large, very, very large Q squared, if my like leading twist factorization holds, then this can be factorized in a leading twist object within a low kernel. And the non-perturbative piece that goes in there is the distribution amplitude for pion and kaon. So what is shown here in this line is just the distribution amplitude of pion and kaon that we have computed in the same setup on the lattice. So I take the lattice computed non-perturbative distribution amplitude, I take the NLO, the coefficients, how to compute this, and this is what you get at 30 GeV squared momentum transfer. So this is sort of, but there are other calculations and people have speculated it that this might happen, but no one has actually made QCD predictions of this before. So to really come to and people have actually really looked at in this context, for example, in this paper, this is one of the state of the art till now, I think, on the PQCD side. So going beyond just a leading twist distribution amplitude picture. So if you take the leading twist, that would be this, similar to like that. And then you can include like a twist 3 2-parton, twist 3 3-parton correlation, twist 4 3-parton correlations in various, and these are very important. And then what you get is this. But the fact that which is very interesting is if you add the multi-parton correlations, if you see a hint of multi-parton correlation, if you add this, so these would be the bands for the kaon and pion, adding up to 4-parton twist 4 3-parton correlations and all possible from this calculation. But what it does, what it shows is that the lattice calculations is essentially a very flat in Q squared. It doesn't change, even almost very little. But I can come close to it by adding I really have to add the multi-parton correlations. I can come close to it, but then the Q squared dependence would be much larger. And I don't know what to say. But and just to make these two lines, so this red lines and this black lines, is essentially saying that I have no PQCD. It's just a fully confined thing. All I have is a vector meson dominance model. So this line, for example, this line is nothing but I take this in the same calculation. I calculate my pion charge radius, which is something like a rho meson mass squared, and I just put it a dipole with that pion radius squared. And that goes through the data pretty good, even, and for the same for the kaon, K-on you need more, like you need the omegas and everything, just the dispersion relations and vector meson dominance. There's no mention of partons or anything. It's just totally non-perturbative descriptions. In the next 6 seconds, I just want to just summarize. So we have just started a new journey. So we are going from 1D to 2D and to eventually the also TMDs, and hopefully at some point, some days, we will also address the multi-parton effects in the lattice calculation. Thank you.
Questions?
Sure. That's for you.
Yeah, use the microphone, please.
Which error bars?
For these form factors, yeah.
This one?
Yeah, all these points, yeah, they have error bar, right?
So these are the lattice QCD error bars. That's sort of what we get. This is including statistical system. Okay, systematic, this is only 2 lattice spacing that we calculated, and everything is whatever we have.
Okay.
Can you do this? Or when can you do this? I would love to see this, right? So.
No, experimentally we can measure, right? For this higher Q square form factor, right?
Yeah.
And then from their measurement, we can have error bar, right?
Yeah, of course.
So I'm trying to understand how did you actually get this error bar?
These are lattice calculations. You get the error bars from lattice calculations or the statistical errors and with all.
Okay, okay, thank you.
Asmita?
Could you please go to the slide showing the transversity calculation?
Okay.
Yeah, thanks. So which one is the lattice calculation?
Oh, the lattice has 3 bands. So these, so let me tell you which are not the lattice calculation. The blue one is the jam, and this one is the Pavia. The rest are the lattice calculations done with using different orders of matching kernel. So there's a LO. So in this point in our calculation, there's almost no difference between going to leading order to next to leading order. If I don't do
question is, what do you mean by leading order next to leading order? This is a lattice. This is not a perturbative calculation, right?
This is what I said in the beginning. Let me try to come back to yes.
Yeah.
So to go to the lattice to the light cone, I need an UV matching because the order of the momentum limit and regularization limits are different. And this matching is done in PQCD, and this is this matching coefficient, and these matching coefficients are computed with various orders. So for the transversity case, leading order means I have no matching. I just take my lattice calculation, that's the thing, and then I correct with an NLO matching, and that's what gives you the NLO. It's essentially, you can think of it, what we calculate on the lattice is also cross-section, some non-perturbative matrix elements. You also need to factorize that. The factorizations of the lattice matrix elements and what you get in the continuum are the different. The difference is the hard coefficients is just a matching.
Marco and then Kefe.
Please put back the slides on the Collins-Hopper kernel. Yeah, it's also impressive, but I would like to understand, I missed what is the technical reason that led you to reduce your noise on lattice?
Yeah, so what we compute in this in the Collins-Hopper kernel, so what you would compute in the way it's computed is 2 TMD wave functions, and the ratio of the 2 TMD wave functions will give you as at a given range of x. This is average over all x. We have to check that it is x independent in this context and so on, which we did. I don't have this, I can show you later. But so now this TMD wave functions, you can also do it, whatever the TMD PDFs, they are separated in longitudinally as well as transversely. Now when you compute, you have to have a gauge link attached to it, a finite gauge link on the lattice. So now you can choose one gauge and fixed a gauge. I do a fixed gauge calculation where I can get rid of the gauge links. The gauge links, when the gauge link becomes very large, it becomes very noisy because it's a long link.
Kefe?
And this choice of gauge in this case is Coulomb gauge, which can go to the light cone.
Swagato, yeah, it's a nice talk. Can you go to page 19? We're about the moments. Now, sorry, not 19, yeah, right, 23, yes, sorry. I presume that these are the moments that you calculate to get a log X. Have you been able to verify this using a direct 3-point function calculation of A and B?
Okay, so
it
let
doesn't depend on
let me clarify you a little bit what these moments are. These are not the moments that I compute by integrating this. This is not what we do. So what I do in this context of the moments is essentially I go to the position space, I do an OPE of the operator and do a position space matching. Okay. I can also do a direct calculation, which, yes. So in this context, we have the verification. So this is done with an ETMC ensemble on the ETMC calculation. ETMC does have the calculations on these ensemble, exactly. I can show you the plots. It's perfect.
Any other questions? Yes?
For which flavor?
These are all U minus D.
Okay. And can you calculate like in the ERBL region? I mean, if we set non-zero zeta.
Yes.
Okay.
We haven't done it, but we can.
Okay, great. Very nice result. Thank you.
Okay, if there are no more questions, oh, Alessandro?
Oh, okay.
So very interesting results, and especially the Collins super is impressive. But no, if you stay back to the H calculation, okay. So how does it compare? I don't think you showed us a comparison with the unpolarized PDF, right? So you showed a comparison
this is the unpolarized PDF.
But that's
in that calculation.
In the calculation, but you don't show the comparison with phenomenology. The transversity case, but for the...
yes, I do have, I mean, not in this calculation, the PDF calculation I did, I mean, okay, so before this, in the same setup, ETMs calculated the PDF, which is a separate calculation. I have my own calculations of PDF, unpolarized PDF, I can show you later.
And how does it compare, qualitatively speaking? I mean,
qualitatively it compares okay, but we can never reach the precision of what you get. I mean, what you will get in the full unpolarized speed. That's way. I mean, it's nothing that really stands out obviously wrong. It will compare okay and qualitatively.
Okay, if there are no further questions, we can thank Swagato again.
Thank you.